Have you ever wondered why bread turns golden and crispy when you toast it? Well, it's not just about the heat. It's about the magic of chemistry that's happening right in your kitchen. Every time you toast a slice of bread, you are witnessing a fantastic display of chemical reactions at work. Let's dissect this seemingly ordinary process and reveal the extraordinary science behind it. When you pop a slice of bread into your toaster and push down the lever, the heating elements start to glow, producing heat. This heat isn't merely warming your bread, it's actually causing a complex chemical reaction known as the Maillard reaction. Named after the French chemist Louis-Camille Maillard, who first described it in the early 20th century, this reaction occurs when the heat causes the sugars and proteins in the bread to interact. These compounds break down and then recombine in new ways, creating hundreds of different flavor and aroma compounds that give toasted bread its distinctive taste. But what about the color? Well, that's part of the Maillard reaction too. The new compounds formed during this reaction include melanoidins, which are brown pigments. These melanoidins are what give toasted bread its appealing golden brown hue. And the texture? That's also a result of the Maillard reaction. The heat causes the water in the bread to evaporate and the sugars to caramelize, resulting in that deliciously crispy crust. Isn't it fascinating to think that something as simple as toasting bread involves such intricate chemistry? It's a perfect example of how chemical reactions are not just confined to laboratories and textbooks. They're happening all around us, all the time, even in something as mundane as making breakfast. So, the next time you're spreading butter on a warm, crispy piece of toast, take a moment to appreciate the magic of chemistry that made it possible. Remember, every time you're making toast, you're actually observing a chemical reaction right in your kitchen. But what exactly is a chemical reaction, you may ask? Well, let's dive right in. A chemical reaction, simply put, is a process that transforms one or more substances into different substances. It's like a grand play happening on a microscopic stage, where the actors, or reactants, undergo a dramatic change to become completely new characters, or products. Imagine you're a master chef, and your ingredients are the reactants. You mix them, heat them, stir them, and voila! You've created a delicious dish, which is the product of your culinary reaction. Now, this may not be a chemical reaction in the strictest sense, but it helps illustrate the concept. Now, just as there are different genres of plays, there are different types of chemical reactions. Let's look at a few. First, we have combination reactions. These are like romantic plots where two reactants come together to form one product. It's as if two actors have become inseparable, creating a single character that is entirely new. Then, we have decomposition reactions, which are the exact opposite. They are like dramatic breakups, where a single reactant splits into two or more products. It's as if a character has revealed multiple hidden personalities. Next up are displacement reactions. These are the plot twists. Here, one reactant takes the place of another in a compound, like a surprise character swap in the middle of the story. And finally, we have redox reactions. These involve both reduction and oxidation, the gaining and losing of electrons respectively. It's like a thrilling exchange of power, where characters gain or lose their strengths. So, you see, chemical reactions are not just dry, scientific phenomena. They are dynamic, exciting processes full of change and transformation. They are at the heart of everything, from the food we eat, to the air we breathe, to the very cells in our bodies. Therefore, a chemical reaction is like a magical transformation, turning one substance into another. It's a dance of atoms, a play of elements, a symphony of change, and we are all part of this grand performance. Now that we know what chemical reactions are, how do we represent them? Well, that's where chemical equations come in. They're kind of like the secret language of chemistry, allowing us to describe what's happening in a chemical reaction in a concise and standardized way. Think of a chemical equation like a snapshot of a chemical reaction. On one side, we have the reactants, the substances that are about to undergo a change. And on the other side, we have the products, the substances that are formed as a result of this change. Now, in this snapshot, we use different symbols to denote the state of these substances. The symbol S is used for solids. It's like the ground beneath our feet, stable and firm. L is for liquids, just like the water in a flowing river. Then we have G for gases, representing the air around us, free and expansive. And finally, we use AQ for substances that are dissolved in water, like sugar in your morning tea, making it an aqueous solution. But there's more to a chemical equation than just reactants and products. We also have the arrow, which indicates the direction of the reaction. On the left side of the arrow, we have the reactants. They're like the ingredients in a recipe. And on the right side of the arrow, we have the products, the delicious dish that results from combining those ingredients. But remember, in chemistry, unlike in cooking, we can't just add a bit of this or that. No, in a chemical reaction, the quantity of matter is conserved. That means the number of atoms of each element in the reactants must be equal to the number of atoms of the same element in the products. This is what we call the law of conservation of mass. So, in a nutshell, a chemical equation gives us a lot of information. It tells us what substances react, what substances are produced, their physical state, and the proportions in which they interact. So a chemical equation is like a recipe for a chemical reaction. But how do we make sure our chemical recipe is balanced? In the world of chemistry, there's an essential principle we must always abide by, the law of conservation of mass. Think of it like a universal rule that says, what goes in must come out. This law states that matter cannot be created or destroyed. It can only be transformed. So, in a chemical reaction, the total mass of the reactants or the ingredients must equal the total mass of the products or the result. Now, let's break down how to balance a chemical equation. Imagine it as a seesaw at a playground. On one side, we have our reactants. On the other side, we have our products. To keep the seesaw balanced, we must have the same amount of each type of atom on both sides. Let's take the chemical equation for the reaction of hydrogen and oxygen to form water. It's written as H2 plus O2 equals H2O. At first glance, it might seem balanced, but let's look closer. On the reactant side, we have 2 hydrogen atoms and 2 oxygen atoms. But on the product side, we have 2 hydrogen atoms and only 1 oxygen atom. This equation is unbalanced. The seesaw is leaning towards the reactant side because there are more oxygen atoms there. So how do we balance it? It's quite simple. We add a coefficient in front of H2O to indicate there are 2 water molecules, changing it to H2 plus O2 equals 2H2O. Now we have 4 hydrogen atoms and 2 oxygen atoms on both sides. The seesaw is balanced. Remember, the key to balancing chemical equations is to adjust the coefficients, not the subscripts. The subscript tells you the number of atoms in a molecule, while the coefficient tells you how many of those molecules there are. And just like that, you've balanced a chemical equation. It's like solving a puzzle. Why should we care about chemical reactions and equations, you might ask? Well, let's delve into why understanding these concepts is not just critical for acing your chemistry exam, but also carries substantial significance in our daily lives and various professional fields. First off, consider the field of medicine. The development of life-saving drugs and treatments is fundamentally rooted in chemical reactions. For example, chemotherapy, a common treatment for cancer, involves the use of drugs that initiate chemical reactions to kill cancer cells. Without a deep understanding of chemical reactions, these advancements in medical treatments would not be possible. Shifting our focus to environmental science, chemical reactions play a crucial role here as well. They are at the heart of processes like photosynthesis, where plants convert sunlight into food, and decomposition, where organic matter breaks down into simpler substances. Understanding these reactions is key to tackling environmental challenges, such as climate change and pollution. Now let's talk about technology. From the battery that powers your smartphone to the fuel that propels rockets into space, chemical reactions are everywhere in technology. The lithium-ion batteries that are prevalent in our electronic devices operate based on a series of chemical reactions. Similarly, rocket fuels undergo a combustion reaction, releasing the energy needed to propel the rocket upwards. Even in the culinary world, chemical reactions are at play. The browning of toast, the curdling of milk, the rising of bread, all these are examples of chemical reactions that occur during cooking. Understanding these reactions can help us become better cooks and appreciate the science behind our food. In essence, Chemical reactions and equations are the backbone of many phenomena that occur in our world. They are the silent workers, tirelessly shaping the world around us, often without us even noticing. So chemical reactions and equations are not just confined to your chemistry textbook. They're all around us and shape the world we live in.